Alright, so in this video we're going to talk about creating an interval estimate for a population proportion. So again, very similar to the previous two examples, you have your point estimate and then you add and subtract to and from that your margin of error. So similar equation right now. So the thing is we're back to the z, using z, the standard normal distribution. So I don't know if you remember this. I can't remember if I mentioned it actually explicitly in a video. But in Chapter 7, we did learn that the sampling distribution of p hat or p bar can be approximated by a normal distribution whenever n times p is at least 5 and when this is also at least 5. So typically, just as long as you have a big enough sample size, you can use the standard normal distribution, the normal distribution. So we're back to the z. I think I showed where this comes from, the standard error for this. I think I showed you where that comes from in a video, I think back from Chapter 7 or maybe whenever we talked about discrete probability. So if you want me to talk about that again, if I didn't do a video, just let me know. I have no problem doing that. So again, it's very similar in concept, an equation. So let's just do an example. Let's say that we survey 900 golfers and we want to know, are they satisfied with tee times at, when they go to golf. And let's say that we find that 396 of them say that they're not, or excuse me, they are satisfied with tee times, and the rest were not. So it's basically yes or no. So let's look at the data. The data are in the Chapter 8 practice file under the proportions tab. So again, notice that there are 901 rows, so I think the first one is a label, so there's 900 observations. So again, that would be too much to count. 1, 2, 3, 4, 5. You're going to be here all day. So we can actually use some functions in Excel to count how many yeses there are. So you can do equals count if, and it says counts the number of cells within a range that meet a given criteria. So we do open parentheses and it asks for two arguments, the range and the criteria. So the range is our data. So let's highlight our data. And then the criteria, right, what has to happen. So we want all of the cells, we want Excel to count the cells that have yes in them. So because they're characters, it's words, we have to put it in quotes. So we put yes in quotes, and I think it's case sensitive. So yes, capital Y, lowercase es, close our parentheses and hit enter, and look at, we get our 396, which is what is given in our example. We know that there's 396 who said yes. So in terms of proportions, right, that's just divided equals that number divided by our sample size, which is 900. So we know that 44% are satisfied with tee times. So we have that. Another way you can do that is equals that value 396 divided by the count. So again, I mean, we know that there's 900. We can look at this and see 901, so we know it's 900. But another function in Excel is another count function, but this time instead of count if, it's count A. So count A, this function, it counts the number of cells in a range that are not empty, right? So if we select that, right, we get the same number. So it's going to count, and it's going to count all the cells that have something in it. So all of these have data. So it's another way to count. You just have to be careful if there's missing data, because then obviously it wouldn't count some. So that might affect the statistics and what you do. So just be aware of those types of things. So this is our proportion value. So we have to, let's go back. We have our proportion, we need to know n, we need to know our standard error, all these types of things. So let's go through and calculate these. So we already know n is 900. Z, so we have to calculate our z. I didn't put this in here in the example, but let's just assume that we're using 95% confidence intervals. So again, that's norm.s because we're back to the standard normal. Z, oops, I'm sorry, I meant to put inverse. Our probability, right, is 0.025 because we're using 0.95. So 1 minus 0.95 is 0.05. Remember, we got to divide that by 2. So we get 0.025, and that gives us our z value. So then our error, right, so we just calculated our z, so now we have to create our, calculate our standard error. Standard error, right, that is equal to the square root of p times by 1 minus p divided by the square root of n. So honestly, I recommend p, we have p, but also 1 minus p, just because it can get confusing with closed parentheses and making sure that you have everything. So it's a little bit easier if we have p and 1 minus p. So, so what are we doing? We're taking the square root, right, of n. Now, again, it gets a little bit confusing. I like to always have extra parentheses just to make sure I'm not forgetting anything. So I want to do another set of open parentheses just to make it explicit that we're multiplying p, right, p times by 1 minus p, right, close parentheses, that is the numerator. And then we're dividing it by our square root of n, our sample size, close parentheses, right? Oops. Sorry, it's not the square root of n, it's just n. That's our other one. I'm sorry about that. And then, so we just have divided by n, because we have the whole square root already done. And now we can do, remember, we have to close our other parentheses, the one that we originally had. And then we can hit enter. So I hope that was clear what I did. Basically, it's just this equation, right, equals the square root of, and I put extra parentheses. I want to make sure that it's clear that we're multiplying these two values first and then dividing by our sample size. Please excuse my dear Aunt Sally. Everything should work out, but like I said, I always like to be extra careful to make sure that everything is explicit and done in the right order, because it can be very easy to forget parentheses and just have something come up incorrect. So now we have our z, we have our standard error, so now we can calculate our margin of error, which is just equal to, right, our z value times by our standard error. Boom. So now we can create the upper and the lower limits, right? Upper is going to equal our proportion plus the margin of error, and our lower is going to be equal to our proportion minus the margin of error. So that is our interval right there. So again, what does this mean? Why are we doing this? Right, the implications, right, I think we're getting the idea that, okay, we have a formula to plug in a bunch of values to actually create our interval estimate, but ultimately, why does this matter? What is it telling us, right? So this upper and lower values for our interval estimate, basically what the interpretation is that we are 95% confident, right, we use 95%, that between 40.76 and 47.24% of the golfers are satisfied with tee times. So you can kind of use that information to decide, policy or business decisions. So if you know that not even half of the golfers out there are happy with tee time, I don't know. I don't golf. I don't know if that's high, if that's low, if that's expected. But usually with satisfaction, you want people to be satisfied. So if not even half of the golfers out there are happy with their tee times, you might want to do something about that. I think this example was using females actually as a sample. So I don't know if there's difference between females and males in golfing. But anyways, at least that is the implication. That's what we're out to better understand. So I think key takeaways from this chapter, right? We collect data from a sample to better understand the population. Unfortunately, that sample statistic, whether it's the mean or the proportion, may or may not provide a good estimate of the population parameter. Therefore, we use an interval estimate to provide a measure of the precision of the estimate. That is, we can give an interval and a degree of confidence, like 95%, that the true population parameter is somewhere in that interval. So, and then our interval estimate is calculated by taking the point estimate, right, our population mean or proportion, and adding or subtracting to and from it the margin of error. And that's more or less this chapter.